Okay, now we're going to talk about a very important concept, which is the momentum. Specifically, we're going to start with linear momentum, and then we're going to talk about angular momentum. So the momentum part, please do not confuse this with, it's not the same as moment. It is not the same. Moment is force times distance. Momentum is mass times velocity. Okay, so momentum is a mass times velocity. But in order to be linear momentum, the velocity has to be in the rectilinear frame of reference. So going back to our equations of acceleration or equations of Newton, the force is the mass times the acceleration of the mass. And this is for a single particle or single system. If you have many planets, many particles, many systems, then each force or each mass will have its own um, momentum. But at the end, the system will have a conservation of momentum that you might see later if you go through engineering classes like fluids and solid mechanics, etc. So momentum is given by the capital letter L, which is a vector because of the velocity part. So the change of um, the velocity, actually this is a typo in your book, is not mass times acceleration, is mass times velocity. So this is the change in time with your space. Okay, so the linear momentum of a particle is zero if the particle remains at a constant magnitude of direction. If it doesn't change velocity, it's going to be zero. But if there's a velocity, then momentum exists. Okay, so that is opposite to angular momentum of a particle, which is given by the capital letter H. And please do not confuse with magnetism. Capital H is reserved mostly for magnetic fields, but in this case, we're going to call it angular momentum. Sometimes they refer it with Greek letters because of the confusion here, but in this case, let's call it H since we don't have any magnetism in this dynamic mechanics class. R, we know is that this as a vector is the distance from a point O or point in your reference system, and this is going to be cross mass times velocity. Okay, perfect. So the cross, if you remember from statics, is product of vectors, which if you consider the point P has a distance r, the distance r with respect to O, and then the particle P is moving in an angular fashion, the mass times velocity of that point with respect to O, of course given an angle with respect to the radial position, that can be computed given your cross product, which is Rm giving you momentum V. So this part is the distance, mass, velocity, sine of the angle. Okay. Sometimes the angle is not known, so what we do is we compute this product using vectorial products. So this is the cross product, remember? So I, J, K for the x, y, and z coordinates. X, y, z coordinates is the point of the distance, and the momentum components of Lx, Ly, Lz. Okay, so I apologize, this is supposed to be Lx. Perfect. Basically, the cross product of I, J, K times your coordinate system, your point in space, this point, and your Lx, Ly, Lz is basically the mass times the velocity at x, mass times velocity at y, mass times velocity at z. That's this. You compute that, and that will give you the angular momentum. If you do know the sign, in planetary orbits, that sign is known. You might go this route. So r times mass, the velocity in angular direction, that is actually the mass times the radius squared, and the delta, the change in the angle squared. Okay, so there's a mapping here. We go from phi to theta, where theta is for the change from your coordinate system from rectangular to polar. The angle phi, this angle, is from the p change in direction, the particle change in direction. But this theta is with respect to the origin. So this is why this is the kinematics. All right, so all this is in the kinematics. All right. Well, let me please change that so we can see it again. Okay, perfect. So the angular momentum with respect to time is the cross product of r with respect to time cross the mass times the velocity, which is what we have right here, plus the, remember this is a chain rule, r, the distance, cross the mass times the derivative of the velocity. And this is because it's a chain rule, right? We're trying to derive the angular momentum with respect to time. In this case, we're doing that because the derivation of velocity will give us an acceleration term. All right, so all that is equal to a velocity vector cross a mass times this velocity plus r cross mass times the mass of the particle times acceleration. So we have velocity here, they're exactly the same, which they came from this right here. And that part, remember, because the change in direction with respect to time is a velocity. And this part came from the change in velocity with time, which is acceleration. So, long story short, this is a long discussion just to tell you the angular momentum. The derivation of the angular momentum is actually the distance r times the summation of all the forces. This is another vector, this is a summation from I to n of all the forces that you have in your system. Okay? And in this case, now we're going to be talking about the kinetics, because now we're interested in the forces. So just notice that if you want to know the movement of the particle with respect to time, you can find your forces. If you want to find your position at any time with respect to the coordinate system, you can do your kinematics. Let me cancel that again. And lastly, the comment that we need to mention here is that this is from the second Newton law of Newton's law, Newton's second law. And that is because the sum of the moments about the origin of the forces acting on the particle is equal to the rate of change of the angular momentum of a particle. Okay, so remember that we have three laws. We've seen the third law left and right, that the force of a system is equal to the mass times its acceleration, but also the second law is that a particle or a system is going to stay at that state, is going to continue at that state unless there's a change in it in the state given by a force or given by an external disturbance. So the first law, we also talked about the first law, which is with respect to the coordinate frame of references, the inertial coordinate frame of references, that a system is going to stay as it is unless it's disturbed. All right, so the conservation of angular momentum is similar. We talked about the linear momentum, and we mentioned the angular momentum, which is L. The conservation of angular momentum is when only forces acting on a particle directed or away or towards the origin So this is very useful because we use this for satellites, for space missions, for aerospace physics. Okay, so again, we have a force on a particle P, and that force is directed towards point O, like a gravitational force, for instance, on a rotational body. So if we have a distance r to P, that particle P has a mass and an acceleration and is changing its direction with an angle phi with respect to the original r. That we talked about this in a previous video. Remember that we did the r dt, and then we said that this is point O and point A and point B. We're going back to this. Okay, there's an original RO, which we called A, and R is called B in that video, where the original position of the particle is exactly the mass times the initial velocity, and its initial change in direction is given by phi sub 0. So given that, since the line of action of the central force passes through the origin, then we know that the conservation of angular momentum is 0, which is a very important aspect of this whole chapter. If you don't have conservation, it's because your mass is changing, because you're losing mass or because you're gaining mass, but otherwise you'll have a constant conservation of angular momentum. Now, the position vector and motion of the particle are in the plane perpendicular to to the linear momentum. To the angular momentum, I apologize. To the linear momentum is L, angular momentum is H. It's perpendicular to the angular momentum. This is because to get here, we had to do the cross product. Remember, the cross product will be a perpendicular vector to your plane. Well, and that is because as we said before, we would do a cross product, which is the sine, is given by the sine of your angle. So if you have the angle, you can go this route. If you don't have the angle, is when you have to do your cross product of x, y, and z with respect to your angular momentum. Okay? So from the conservation of angular momentum, we can derive the equations of acceleration and velocity. Again, picture angle theta. There's a force acting on the radial component. P has a length of r d theta. So the area, because it's a triangular shape, is the 1/2 of radius squared d theta. Okay, and then if you define dA dt, so basically find the derivative of this guy, you have to do a chain rule because r and theta are changing. You're gonna have 1/2 of r squared d theta dt, and in that case, you're gonna have this function. For this first part, we assumed that r is fixed. So notice that for this part, we only derived with respect to the angle. This is called the areal velocity. But also, for a body moving under a central force, that there's a constant equals to r squared theta dt. That's the velocity, right? The angular velocity. And when a particle moves under a central force, its areal velocity is constant. Do we know that? So this is because even though you're accelerating because of the change of rotation, your velocity on the periphery is constant. So from that, we go back to the original equations that we already know. If we consider r and theta in polar coordinates, and we do a summation of the forces that are applied to that particle, we get the second derivative of r with respect to time plus minus r times the change in theta squared. That is respect to the radial direction. Respect to the the angle here, theta, we have the acceleration theta, so the mass is the same for both. What changes is the component of the acceleration. So mass stays the same. Now we're gonna have r theta squared plus 2 r dot and theta dot. We already know that. But I'm showing you this because the result can also be derived from angular momentum. if you start from here, which is the mass r squared theta dot, which is what we had last slide, then r is a constant. We mentioned that for the case first instant when r is a constant. It's not changing r, it's just changing the angle. You derive that quantity, then you get to this, okay? And in that case, you can find that we have 2r times r dot and theta dot. Okay, so we can get rid of one of them and we get to the original equation that we had before. Okay, so let's look at this special case, which is the gravitational force exerted by the sun or a planet. So this is the gravitational force. This is basically the gravity force attracting two particles. So there's a mass m and there's a different mass, little m. We always have to have radius squared, and g is the gravitational constant. Okay, so this is four forces attracting each other. This is not the gravity on Earth. A gravity on Earth is a special case. This constant has a value of 66.73 times to the 10 negative 12. And the units are a volume in meters cubic, kilograms per second squared. If you remember, gravity on Earth is 9.81 meters per second squared. Well, here we don't have we have meter cubic and we have kilograms. So that's why the gravity of each planet is a special case, because you factor in masses and volumes. So this is a constant for any gravitational force, and is a universal constant. And in English imperial system will be feet cubic. So sorry, it's going to be feet to the fourth power, pound second to the fourth power. Okay. So for a particle of mass m on Earth, we use that m. This is going to be a force, right? Remember, force equals mass times gravity times acceleration. So mg, the gravity, just the gravity portion of it, is 9.81 meters per second. It's because it's already factoring distances and gravities and other masses. So if you want to look at why we have 9.81 meters per second from this gravitational constant, you should look in the book or the references online. But I want to go ahead and do this example. So a satellite is moving under a central force. Its angular momentum is constant. So that's a very important part. If the angular momentum is constant, then we know that the mass is not changing. Equate the angular momentum at A and B and solve the velocity. Basically what they're saying is that since the mass is the same, here the velocity is going to be slower and here the velocity is going to be faster because there's a change in direction. Okay, but the mass is the same. So we start from, since we're not given any vectors, we're going to use the equation where we're giving r, m, v, and sine of the angle. So we want to use a point, we want to find a point A and point B. They're telling us that we know that the velocities, the angular momentums are the same. So r, m, v at A equals r, m, v at B. So the masses are the same. Therefore, we simply have to find for velocity v, and they give us every single aspect of it. So they're giving us the velocity, which is 18,820 miles per second. The radius I at A is 3,960 plus 240 miles, which is this distance. And at B, from O, is 3960 plus 2340 miles per miles is this distance, right? So I apologize, I should have given more information for this because I just noticed that I wrote down the problem, but I didn't give you the values until the answer was here. So yes, they're giving us the velocity at A, which is pretty fast, 18,800 miles per hour. And they're telling us that the distance RA is given, so they actually give us the distance, and the actual distance at B is also given, which is this value. So you only need to find your RA and your distance at A and your distance at B. This is A and this is B. When you do that, you'll find that the velocity at B is 12,550 miles per hour. So as you noticed, the velocity here is greater than the velocity here, but the moment is conserved because this angle here is sharp and different than the angle here. Okay, what I mean is that even though this is a circumference, well, this is an elliptical shape, then this velocity is going to be faster because of the gravity effect. It's going to be faster, and then it's going to be slower over here. It's going to be faster, and then it's going to be slower. So the only changes that apply here are the changes in distance and the changes in velocities. Masses are the same. So this value of RA is different than this value of RB, obviously, is smaller. So the velocity here has to be higher and at A, and the velocity at B has to be slower because the distance is greater.